What if I told you that you're sitting there right now, are essentially trapped in a cosmic prison, and the walls of that prison are closing in faster than you think? Not because of some evil force, but because the universe itself is expanding so rapidly that 94% of the observable cosmos is already forever unreachable, no matter how fast we travel or how advanced our technology becomes. That number grows every single second. Right now, as you watch this video, galaxies are slipping beyond an invisible horizon called the cosmic event horizon, vanishing from our reachable universe forever. In fact, by the time you finish watching this video, approximately 20,000 stars will have crossed that threshold, becoming permanently inaccessible to humanity for all time. We're not just talking about difficult to reach. We're talking about physically, fundamentally, absolutely impossible to ever reach, even if we could somehow travel at the speed of light itself. Here's the shocking truth that scientists discovered only in 1998, work that earned Saul Perlmutter, Brian Schmidt, and Adam Rees the Nobel Prize in Physics in 2011. The universe's expansion isn't just continuing, it's accelerating. Dark energy is pushing space apart faster and faster. And this acceleration means that the future of space travel is far more limited than any science fiction story ever told you. The window of opportunity for humanity to explore the cosmos is not eternal. It's closing, but here's where it gets even more disturbing and fascinating. The question of how far humans could travel into space isn't just about distance or technology. It's about time, biology, physics, and the fundamental nature of reality itself. And the answers will force you to completely reconsider what it means to be human, what it means to explore, and what our actual place in this universe truly is. Before we dive deep into this cosmic journey, I need you to do something. Hit that like button right now. It actually helps more people discover these mind-bending truths about our universe. And subscribe, because we're about to go on a 3.5-hour journey that will fundamentally change how you see our place in the cosmos. Also, drop a comment telling me what country you're watching from and what time it is for you right now. I'm genuinely curious to know how far across our own planet this message reaches while we discuss reaching across the universe. Are you watching from Brazil at midnight? India in the early morning? Australia during lunch? Let me know. Now, let's begin with what seems like a simple question, but has an answer that will blow your mind in ways you never expected. To understand how far humans could travel into space, we first need to establish what we're actually measuring. And this is where most people's understanding completely falls apart, because space travel isn't like traveling on Earth at all. On Earth, if you have enough fuel and time, you can theoretically reach any point on the globe. The rules are simple: distance, speed, time. But space? Space plays by rules so alien to our intuition that they seem like science fiction, except they're verified, tested, and absolutely real. Let's start with the basics, but I promise even these basics will surprise you. Our universe, the observable universe, is approximately 93 billion light-years in diameter. Now, you might be thinking, wait, I thought the universe was only 13.8 billion years old? How can we see things 46.5 billion light-years away in each direction? Congratulations, you've just stumbled onto your first cosmic puzzle, and the answer reveals something profound about the nature of space itself. The universe isn't just a static container where things move around. Space itself is expanding. Think of it like this. Imagine you're an ant on the surface of a balloon, and someone is inflating that balloon. Even if you never move a muscle, you're getting farther from other ants on other parts of the balloon, because the balloon's surface, the space itself, is expanding. That's our universe, except in 3 dimensions instead of 2. This expansion happened incredibly fast in the early universe, during a period called cosmic inflation, discovered and described by Alan Guth in 1980. In the first fraction of a second after the Big Bang, we're talking about 1036, Seconds, the universe expanded by a factor of at least 1026. That's a 1 followed by 26 zeros. The universe went from smaller than an atom to larger than a galaxy in less time than it takes light to cross the nucleus of an atom. But here's the critical part that affects everything we're going to discuss. Space can expand faster than the speed of light. This doesn't violate Einstein's speed limit because Einstein's relativity says that nothing can move through space faster than light. But space itself isn't moving through anything. It's the thing that's expanding. It's like the rule book says, no player can move faster than X, but the playing field itself is stretching. So when we ask, how far can humans travel into space? We're really asking, how much of this expanding universe can we actually reach before the expansion carries it away from us forever? Let me give you the first mind-blowing answer. We can never leave our local supercluster of galaxies. Ever. No matter what technology we develop. The Laniakea supercluster, that's the poetic name astronomers gave to our local collection of 100,000 galaxies, is our permanent cosmic home. Everything outside of it is currently receding from us faster than we could ever reach it, even if we left today traveling at the speed of light. Think about that. We've mapped a universe containing 2 trillion galaxies. We can see them. We can study them. We can watch them being born and dying. But 99.99999% of them are already forever beyond our reach. We're like prisoners who can see through the bars, but never touch what's on the other side. But let's not get ahead of ourselves. Before we talk about traveling to other galaxies, we need to understand the staggering challenge of even leaving our own neighborhood. And our neighborhood? That's our solar system. And even that tiny speck of the universe presents challenges that most people have absolutely no concept of. The solar system is vast in a way that human brains aren't equipped to understand. We evolved to understand the distance from our cave to the watering hole, from the watering hole to the hunting grounds. We did not evolve to understand cosmic distances. So let me give you an analogy that might help, and this one is going to be your first think of it like this moment. If Earth were the size of a basketball, the moon would be a tennis ball about 23 feet away. That's the farthest humans have ever traveled, 23 feet in this scale. Mars would be about 2 miles away. Jupiter would be 10 miles away. Pluto would be about 80 miles away. And the edge of our solar system, the heliopause where the sun's influence ends, that would be about 160 miles away from our basketball Earth. Now, in this scale, where is the nearest star, Proxima Centauri? Take a guess. Remember, Pluto is 80 miles away in this scale. The nearest star would be approximately 6,000 miles away. That's the distance from New York to Berlin. That's the scale of the problem we're dealing with. The fastest spacecraft we've ever built is the Parker Solar Probe, which reached speeds of 430,000 miles per hour. At that speed, which is already incomprehensibly fast, that's New York to Los Angeles in 6 minutes. It would still take about 6,700 years to reach Proxima Centauri, our closest neighboring star system. The probe, by the way, is named after Eugene Parker, the physicist who predicted the solar wind back in 1958, a prediction that wasn't confirmed until spacecraft could actually visit space and measure it. Parker lived to see his probe launched in 2018 at age 91, the first NASA spacecraft named after a living person. Now you might be thinking, okay, so space travel is slow, but we'll just build faster ships. And here's where the laws of physics start to really, genuinely hurt us. This is going to be your first moment where you realize the universe doesn't care about our dreams. Speed isn't free. Every bit of acceleration requires energy, and the amount of energy required grows exponentially as you approach the speed of light. According to Einstein's special relativity, as you go faster, your mass effectively increases, meaning you need even more energy to go even faster. It's like trying to run through water that gets thicker and thicker the faster you go. You can never quite reach light speed because doing so would require infinite energy. Let me make this concrete with actual numbers, because the math here is what really hammers home the impossibility. To accelerate a single kilogram about the weight of a laptop to 90% of the speed of light would require about 1.8 times YOI joules of energy. That's approximately 4,300 megatons of TNT, the largest nuclear weapon ever detonated. The Soviet Tsar Bomba was 50 megatons. So to accelerate a laptop to 90% light speed, you'd need the energy of about 86 Tsar Bombas. Now, a spacecraft capable of carrying humans would need to weigh at least several tons. And here's the brutal part. You need to carry enough fuel to slow down when you get there, which means you need even more fuel to accelerate all that extra fuel. This is called the tyranny of the rocket equation, and it's the equation that makes engineers cry. The rocket equation shows that the fuel requirements grow exponentially with the desired speed and distance. It's not linear, it's exponential. But let's say, just for the sake of argument, that we somehow solve the energy problem. We've got unlimited power, we've got perfect engines, we can accelerate to whatever speed we want. We're going to travel at 99.9% of the speed of light to reach distant stars. Congratulations, you've just created a new problem that will kill you in ways you never imagined. Space is not empty. Space contains dust, gas, particles sparse, yes, but they're there. At normal speeds, these particles are harmless. But at 99.9% of the speed of light, every single hydrogen atom you hit impacts your spacecraft with the energy of a particle in a particle accelerator. The interstellar medium would essentially become deadly radiation. A single grain of dust, something you wouldn't even notice on Earth, would hit your spacecraft with the energy of a bomb. Your spacecraft would need shielding so heavy that it would make the mass problem even worse. And all of that shielding would need to be accelerated too. So here's where we stand so far, just trying to leave our solar system and reach the nearest stars. We need impossibly huge amounts of energy. We need to solve the radiation shielding problem, and we need to accept journey times that span multiple human lifetimes, even at relativistic speeds. And we haven't even talked about the human problem yet. That's coming, and it's going to blow your mind. But first, let me give you a retention hook, because what I'm about to tell you in the next section will make everything we just discussed seem almost trivial. We've talked about the engineering problems of space travel. But what if I told you that the real limiting factor isn't engineering at all? What if the real problem is that the human body, in its current form, is fundamentally incompatible with interstellar travel? What if evolution designed us so specifically for Earth that leaving it for extended periods is essentially a death sentence? Stay with me, because the biology of space travel is where things get really disturbing. The human body is a magnificent machine, but it's a machine built for one specific environment, Earth's surface, with its specific gravity, its specific radiation environment, its specific atmospheric pressure. Evolution spent 4 billion years fine-tuning life for this one narrow set of conditions. Taking that biology into space is like taking a deep-sea fish and expecting it to survive in a desert. Let's start with what happens to the human body in microgravity, because this is where the problems begin even before we leave Earth orbit. And I'm going to tell you things that NASA has learned over decades of space station research, things that fundamentally challenge whether long-term space travel is even possible without radically changing what we are. In microgravity, your bones begin to dissolve. This isn't an exaggeration or a metaphor. Your bones literally lose density at a rate of about 1 to 2% per month. Think of it like this: osteoporosis, a disease that might take decades to develop on Earth, happens in fast-forward in space. Astronauts on the International Space Station lose bone mass at rates 10 times faster than postmenopausal women with osteoporosis. Why? Because your bones are smart. They're not static structures. They're constantly being broken down and rebuilt by specialized cells. The balance between breakdown and rebuilding is controlled by mechanical stress. When you walk, run, or even just stand on Earth, your bones experience stress from supporting your weight against gravity. This stress signals your bones to stay strong. Remove gravity, and your bones essentially think, hey, we don't need to maintain all this expensive, metabolically costly bone tissue. Let's recycle it for other uses. Your body starts cannibalizing your skeleton. The calcium from your dissolving bones? It goes into your bloodstream, increasing your risk of kidney stones. Several astronauts have developed kidney stones in space, or shortly after returning to Earth. Imagine developing a kidney stone on a 3-year journey to Mars. There's no hospital. There's no surgery. Just you, excruciating pain, and the hope that you can pass it. But wait, it gets worse. Your muscles atrophy at a similar rate. Even with the 2 to 3 hours of exercise that astronauts do every single day on the ISS, and these are people at peak physical fitness doing intensive resistance training, they still lose muscle mass. Your heart, which is itself a muscle, gets weaker and changes shape. It becomes more spherical, less efficient. Your spine stretches out. Without gravity compressing it, the discs between your vertebrae expand, and astronauts grow about 3% taller in space. That sounds fun until you realize it comes with chronic back pain. Many astronauts return to Earth with herniated discs and long-term back problems. Your fluids shift upward. On Earth, gravity pulls your blood and other fluids downward, more into your legs. In space, fluids redistribute toward your upper body and head. This causes what's called puffy face, bird leg syndrome. Astronauts' faces swell up and their legs get thinner. More seriously, this fluid shift increases pressure inside the skull, which can damage the optic nerve. Some astronauts have returned from 6-month missions with permanent vision damage. Their eyeballs literally change shape due to the increased intracranial pressure. And then there's the radiation. Oh boy, the radiation. Earth's magnetic field and atmosphere protect us from the constant bombardment of cosmic radiation. In space, you have no such protection. Cosmic rays, high-energy particles streaming through space paths, through spacecraft hulls, and through your body. They damage DNA, increasing cancer risk dramatically. They can cause cataracts. They damage the cardiovascular system. Some studies even suggest they cause cognitive impairment. On the ISS, astronauts are still partially protected by Earth's magnetic field. They experience radiation doses of about 50 to 200 millisieverts over 6 months. For comparison, a chest X-ray is about 0.1 millisieverts. So 6 months on the ISS is roughly equivalent to 500 to 2,000 chest X-rays worth of radiation. And the ISS is still close to Earth. On a journey to Mars, astronauts would experience even higher radiation levels, estimated at around 300 millisieverts for a round trip. That's enough to increase their lifetime cancer risk by about 5%. But here's the truly terrifying part that recent research has revealed. Cosmic rays don't just damage DNA in the regular ways we understand. Heavy ions in cosmic radiation cause complex DNA damage that our cells struggle to repair. Researchers like Francis Cucinoda, who spent decades studying space radiation at NASA, have shown that the biological effects of cosmic radiation are far more severe than we initially thought. These heavy ions create tracks of damage through tissue, destroying multiple cells in a line, causing what's called a microlesion. Your immune system and DNA repair mechanisms evolved to handle Earth radiation, UV light, natural background radiation. They're not equipped to handle cosmic rays. And we still don't fully understand the long-term neurological effects. Animal studies have shown that cosmic radiation exposure can cause brain inflammation, neuron damage, and behavioral changes. Some research suggests it might even accelerate Alzheimer's-like dementia. So let me paint the full picture of what happens to a human body on a multi-year journey through space. Your bones are dissolving. Your muscles are wasting away despite constant exercise. Your vision is potentially degrading. Your cardiovascular system is changing in ways we don't fully understand. Cosmic rays are shredding your DNA and potentially damaging your brain. And your immune system is compromised by the stress and radiation. And this is all happening in a tiny capsule where you're breathing recycled air, eating freeze-dried food, unable to smell fresh air, feel rain, see a horizon, or experience any of the natural stimuli that humans evolved with. The psychological stress alone is enormous. Research on long-duration missions shows significant increases in stress, anxiety, depression, and interpersonal conflicts. We're talking about crews who are highly trained, psychologically screened, and motivated. Now imagine ordinary people on multi-generational starship journeys. Now, you might be thinking, okay, but we can solve these problems with better technology. Artificial gravity through rotation, better shielding, better medicine. And you'd be partially right. We can mitigate some of these problems. But here's the reality check. We've been sending humans to space for over 60 years now, and we still haven't solved these fundamental biological incompatibilities. The ISS has been continuously occupied for over 23 years, and astronauts still can't stay up there for more than about a year without serious health consequences. A rotating spacecraft to create artificial gravity? The engineering challenges are immense. The structure would need to be enormous to avoid Coriolis effects that would make people nauseous. We're talking about spacecraft, potentially kilometers in scale. And all of that structure needs to be accelerated, which brings us back to the energy problem we discussed earlier. Better radiation shielding? The most effective shielding is mass-thick layers of material to absorb radiation. But mass equals weight equals more fuel required. Some proposals suggest using water as shielding, since humans need water anyway. Kill two birds with one stone. But the amount of water needed for effective radiation shielding would be enormous. We're talking about surrounding the living areas with several meters of water. And here's a problem that most people never even consider: reproduction. If we're talking about multi-generational starship journeys, the only realistic way to reach distant stars with current physics, we need humans to successfully reproduce in space. But we have almost no data on mammalian reproduction in space. The few experiments done with rodents show potential problems with embryonic development. What happens to a human fetus developing in microgravity? We genuinely don't know. The sample size is exactly 0. One Japanese astronaut, Mamoru Mori, half-jokingly raised this question after his space flights. Can humans reproduce in space? The answer is, we don't know, and we can't ethically experiment to find out until we're much more certain it's safe. But this means that the multi-generational starship concept might be fundamentally flawed if human reproduction requires Earth gravity. So here's the brutal truth we've arrived at. In our current biological form, humans are extraordinarily fragile space travelers. We're Earth creatures, through and through. Evolution didn't prepare us for space. It prepared us for the African savanna. Every single biological system in our bodies expects Earth-normal conditions. This is why some scientists are starting to suggest something that might sound like science fiction, but is increasingly being discussed seriously. Maybe the answer to how far can humans travel in space depends on redefining what we mean by human. Maybe biological humans need to be modified, genetically engineered for space travel. Maybe space travelers need to be synthetic, uploaded consciousnesses, or some hybrid of biological and machine. Maybe the distant future of space exploration belongs not to Homo sapiens, but to Homo spatialis humans modified for space. But before we go down that rabbit hole, we need to understand just how far there actually is to go. Because the scale of the problem isn't just biological, it's cosmological. And that's where things get really mind-bending. Let me leave you with this thought as we transition to the next section. Everything we've discussed so far, the engineering problems, the biological problems, Those are the challenges of just reaching nearby stars within our galaxy. Our galaxy, the Milky Way, contains about 200 to 400 billion stars. And we've been talking about the difficulty of reaching even the closest ones. But the Milky Way is just one galaxy. There are 2 trillion galaxies in the observable universe. And here's what will blow your mind. The vast majority of those galaxies are not just far away, they're unreachable. Not difficult to reach. Not, we need better technology, unreachable. Fundamentally, physically impossible to reach because of the expansion of space itself. That's what we're diving into next. The cosmological limits of space travel, the ultimate cage that physics has built around us. Now we need to talk about the universe itself and why it's constructed in a way that makes long-distance space travel infinitely more complicated than most people imagine. We need to talk about the cosmic speed limit, the expansion of space, and a concept that should terrify and awe you in equal measure, the cosmic horizon. Let's start with Einstein. Albert Einstein, in 1905, published his special theory of relativity, which fundamentally changed our understanding of space, time, and motion. Among many revelations, Einstein showed that the speed of light, 299,792,458 meters per second, often rounded to 300,000 kilometers per second, is not just the speed of light. It's the speed of causality itself. It's the maximum speed at which any information, any influence, any effect can propagate through the universe. Nothing with mass can reach the speed of light. As you accelerate an object, its effective mass increases, requiring more and more energy to continue accelerating. To actually reach the speed of light would require infinite energy, which is obviously impossible. Light itself can travel at light speed precisely because photons have no mass. This speed limit has profound implications for space travel. Think of it like this. The speed of light is to the universe what the sound barrier once was to aviation, except the sound barrier could be broken with enough technology and energy. The light speed barrier cannot be broken. It's not an engineering problem. It's a fundamental feature of how space-time works. But here's where it gets interesting and weird. Einstein's speed limit says nothing can move through space faster than light. But space itself can expand faster than light. And it does. In 1929, Edwin Hubble made one of the most important observations in the history of astronomy. Looking at distant galaxies, he noticed that they were moving away from us, and the farther away they were, the faster they were receding. This wasn't because the galaxies were moving through space. It was because space itself was expanding, carrying the galaxies with it. Think of it like this, and this is your crucial analogy. Imagine a loaf of raisin bread dough rising in the oven. You're a raisin, and every other raisin is a galaxy. As the dough expands, every raisin moves away from every other raisin, not because the raisins are moving through the dough, but because the dough itself is expanding. Raisins that are farther apart move away from each other faster because there's more dough between them to expand. This is our universe. The dough is space itself, and it's expanding. The rate of expansion is described by the Hubble constant currently measured at about 70 kilometers per second per megaparsec. Let me translate that into comprehensible terms. For every 3.26 million light-years of distance between us and a galaxy, that galaxy is receding from us at an additional 70 kilometers per second due to the expansion of space alone. Here's where this becomes absolutely critical for space travel. At a certain distance, galaxies are receding from us faster than the speed of light. Not because they're moving through space faster than light, that would violate relativity, but because the space between us and them is expanding so fast that the distance grows at faster than light speeds. That distance, the distance beyond which objects are receding from us, faster than light, is called the cosmic event horizon, or sometimes the Hubble radius. Currently, that's at about 14.5 billion light-years away. Anything beyond that distance is receding from us faster than light. Now you might think, okay, so we can't reach anything beyond 14.5 billion light years. That's still a lot of universe. But here's the absolutely crucial, mind-breaking fact that changed everything in 1998. The universe's expansion is accelerating. Saul Perlmutter, Brian Schmidt, and Adam Rees were studying distant supernova stellar explosions that serve as excellent standard candles for measuring cosmic distances. What they discovered shocked the scientific community so profoundly that it earned them the Nobel Prize in 2011. Distant supernovae were dimmer than expected, meaning they were farther away than they should be if the universe's expansion was constant or slowing down. The only explanation: the expansion of the universe is speeding up. Something is pushing space apart faster and faster, and we don't know what it is. We call it dark energy, which is really just a placeholder name, for we have no idea. But measurements show it's there. Dark energy makes up about 68% of the universe's total energy content, and its effect is to accelerate cosmic expansion. Here's what this means for space travel, and this is where everything we've discussed comes crashing down to a horrifying conclusion. Because expansion is accelerating, the cosmic event horizon is getting closer to us. Not in physical distance, we're not moving, but in terms of reachability. Galaxies that are currently within our cosmic event horizon will eventually cross it and become forever unreachable as acceleration carries them away. Robert Caldwell, a physicist at Dartmouth College, along with colleagues, has calculated the future fate of the universe under accelerating expansion. The picture is bleak. Currently, we exist in what's called the Virgo supercluster, or more recently, the Laniakea supercluster, a collection of galaxies bound together by gravity. Gravity is strong enough within this local group to overcome cosmic expansion. But beyond our local group, expansion wins. Here are the numbers that should haunt anyone who dreams of interstellar travel. In about 100 billion years, every galaxy outside our local group will have crossed the cosmic horizon. The night sky, for whatever civilizations exist then, will be completely dark, except for the merged remnant of the Milky Way and Andromeda galaxies. They're currently approaching each other and will merge in about 4.5 billion years. The rest of the universe will literally disappear from view. But it's actually worse than that. Galaxies don't need to cross the cosmic horizon to become unreachable. They just need to be receding, fast enough that we can't catch up to them even traveling at light speed. That distance is called the cosmic light horizon, and it's currently at about 46.5 billion light years, which is why the observable universe is 93 billion light years across. A paper by Lawrence Krauss and Glenn Starkman in 2000 calculated exactly what percentage of the observable universe we could theoretically reach if we left today traveling at the speed of light. The answer? About 3%. 97% of the galaxies we can currently observe are already unreachable, even if we could somehow travel at light speed starting right now. Let me repeat that because it's so important. 97% of the observable universe is already forever beyond our reach. Even with perfect technology that could somehow achieve light speed travel, and that percentage is shrinking. With every passing second, more galaxies slip across the reachability threshold. The window of opportunity for exploring the universe is closing. Not slowly over trillions of years, but on timescales that are cosmologically quite rapid. Every moment we delay, more of the universe becomes inaccessible. Now let's bring this down to practical scales. Our galaxy, the Milky Way, is about 100,000 light years across. That means even traveling at the speed of light, which we've established, is impossible for anything. With mass, it would take 100,000 years to cross from one side to the other. A journey to the galactic center from Earth would take about 27,000 years at light speed. The Andromeda Galaxy, our nearest major galactic neighbor, is 2.5 million light years away. At light speed, 2.5 million years of travel time. But we can't travel at light speed. Let's be wildly optimistic and say we develop technology to reach 10% of light speed, which would still require overcoming monumental engineering challenges we discussed earlier. At 10% light speed, nearest star, Proxima Centauri, 42 years. Galactic center, 270,000 years. Andromeda Galaxy, 25 million years. And remember, these are one-way trip times. If you want to send information back to Earth, double them. If you want the travelers to return, double them again. But here's where relativity does give us one small, weird mercy: time dilation. According to special relativity, the faster you travel, the slower time passes for you relative to stationary observers. If you're on a spacecraft traveling at 90% of light speed, time passes at about 44% of the normal rate for you. At 99% of light speed, time passes at about 14% of the normal rate. At 99.9% of light speed, you experience only about 4.5% of the time that passes for people on Earth. So in principle, in wild, optimistic, physics allows it principle, you could travel to Andromeda and back in what feels like a manageable time for you. If you could somehow maintain 99.9% of light speed for the entire journey, ignoring acceleration and deceleration, the trip to Andromeda would take 2.5 million years as measured on Earth, but only about 112,000 years of subjective time for you. Still several thousand human generations, but not millions. There's a famous thought experiment called the twin paradox that illustrates this. If one twin stays on Earth and the other travels to a distant star at near light speed and returns, the traveling twin will have aged less than the Earth twin. This isn't just theoretical. It's been measured with atomic clocks on fast-moving aircraft and GPS satellites. GPS satellites have to account for relativistic time dilation, or their positioning calculations would be off by kilometers. So theoretically, a crew traveling at extreme relativistic speeds could cross the galaxy in what feels like a human lifetime to them, even though millennia or more pass on Earth. But notice the tragedy built into this. There's no coming home. Everyone you knew, everyone you loved, your entire civilization would be long dead. You'd return to an Earth utterly transformed, assuming it and humanity even still exist. You would be a time traveler, not just a space traveler, launched forward into a future you have no connection to. This creates what we might call the relativistic exile. Any truly interstellar journey at relativistic speeds is also a one-way journey through time. You can never return to the world you left. You're not just leaving your planet. You're leaving your entire era of history. But let's be honest, we're nowhere near achieving such speeds. The fastest human-made object, the Parker Solar Probe, travels at about 0.064% of light speed at its fastest. We would need to increase our maximum speed by a factor of 1,500 just to reach 10% of light speed. How could we even theoretically approach relativistic speeds? Several concepts have been proposed. 1. Nuclear pulse propulsion. Project Orion. Detonate nuclear bombs behind a spacecraft and ride the shockwave. Seriously. This was actually studied by some of the best minds in physics in the 1950s and 60s. It could theoretically achieve 5 to 10% of light speed. Obviously, there are some practical and political problems with setting off thousands of nuclear explosions. 2. Fusion ramjet, Bussard ramjet, a theoretical engine that scoops up hydrogen from the interstellar medium and uses it as fusion fuel. Proposed by physicist Robert Bussard in 1960, it's elegant in theory, but faces massive practical problems. The interstellar medium is incredibly sparse, and the ram scoop would need to be enormous, potentially thousands of kilometers wide. 3. Antimatter drives. Matter-antimatter annihilation produces pure energy via E equals mc. It's the most efficient energy source theoretically possible. The problem? We can only produce antimatter in particle accelerators, and it takes far more energy to create antimatter than we get back from annihilating it. Current production rates are measured in nanograms. We'd need tons. 4. Light sails. Use powerful lasers or the sun's radiation pressure to push ultra-lightweight spacecraft. This is actually the most feasible near-term option for reaching nearby stars. The Breakthrough Starshot Initiative, backed by Stephen Hawking before his death and funded by Yuri Milner, proposes sending tiny chip-sized spacecraft to Proxima Centauri at 15 to 20% of light speed using ground-based lasers. These probes wouldn't carry humans, they're far too small, but they could reach our nearest neighbor in about 20 to 30 years and send back data. Each of these approaches has profound limitations, but notice what they all have in common. They're concepts, not technologies. We haven't built any of them. We're not close to building any of them. They're theoretical possibilities, constrained by physics, but far beyond our engineering capabilities. And here's the thing that should really drive home the scale of the challenge. Even with perfect propulsion, even if energy were free, even if we could accelerate instantly to any speed we wanted, the universe's geography makes the vast majority of it unreachable due to cosmic expansion. The engineering problems and the cosmological problems compound each other. We're trapped not just by our technology, but by the fundamental structure of space-time itself. So when we ask, how far can humans travel into space, we have to contend with multiple limiting factors working together. 1. The speed of light as an absolute limit. 2. The enormous energy requirements to approach that limit. 3. The biological fragility of human bodies. 4. The expansion of the universe carrying distant destinations away from us. 5. The acceleration of that expansion due to dark energy. Each one of these would be challenging on its own. Together, they create a cage far stronger than most people realize. But here's where I'm going to flip the script on you. What if I told you that, despite all of these limitations, there might be loopholes? Not in the sense of magic or fantasy, but actual theoretical physics that suggests ways around these problems. Ways that are consistent with relativity and our understanding of space-time. That's what we're exploring next, and I promise it will blow your mind in ways that make everything we've discussed so far seem almost conservative. We're about to talk about wormholes, warp drives, and the question of whether physics actually allows what amounts to faster-than-light travel. Subscribe if you haven't already, because this is where things get really wild. Now let's talk about the loopholes. Because as bleak as everything I've just described sounds, physics beautiful, weird, mathematical physics doesn't actually forbid faster-than-light travel in the way most people think. It forbids moving through space faster than light. But it says nothing about warping space, creating shortcuts through space, or otherwise cheating the system. This is where we get into what's called exotic solutions to Einstein's equations. And I want to be very clear here. Everything I'm about to describe is consistent with general relativity. These aren't science fiction fantasies. They're mathematical solutions to Einstein's equations that actually work on paper. The question is whether they can work in reality, and that's where things get complicated and controversial. Let's start with wormholes, officially called Einstein-Rosen bridges after Albert Einstein and Nathan Rosen, who first described them mathematically in 1935. A wormhole is exactly what it sounds like, a tunnel through space-time connecting two distant points. Think of it like this, and here's your next crucial analogy. Imagine space is a sheet of paper. Point A and point B are on opposite corners of the paper. Normally, to get from A to B, you'd have to travel across the paper surface. But what if you folded the paper so that A and B touch, and punched a hole through? Now you can travel from A to B almost instantly through the hole, instead of across the surface. That's a wormhole. The math works. Solutions to Einstein's field equations that describe traversable wormholes exist. And this is a massive, but these solutions require something called exotic matter or negative energy to hold the wormhole open. Without it, the wormhole would collapse faster than anything could pass through it. What is exotic matter? It's matter with negative energy density, matter that has less than nothing in terms of energy. In everyday experience, we never encounter negative energy. Everything has positive energy. Even a vacuum-empty space has positive energy. This is quantum field theory, and it gets weird, but trust me on this. Exotic matter would have negative energy, and it would have bizarre properties like negative mass, meaning it would fall upward in a gravitational field. Here's the critical question. Does exotic matter exist? We don't know. We've never observed it directly. However, there's a quantum mechanical effect called the Casimir effect, first predicted by Dutch physicist Hendrik Casimir in 1948 and experimentally confirmed in 1997. That creates something like negative energy. If you place two uncharged, conducting plates very close together in a vacuum, they attract each other. This happens because the vacuum between the plates has slightly less energy than the vacuum outside the plates, a kind of negative energy relative to normal vacuum. Some physicists, like Kip Thorne at Caltech, one of the world's leading experts on general relativity, and the physicist who consulted on the movie Interstellar, have suggested that perhaps the Casimir effect or other quantum phenomena could provide the exotic matter needed for wormholes. But we're talking about incredibly tiny effects. The Casimir force is measurable only at nanometer scales. Creating a wormhole large enough for a human to pass through would require amounts of exotic matter we have no idea how to produce. We're not talking about difficult engineering. We're talking about something that may be fundamentally impossible given the laws of physics. Moreover, even if we could create a wormhole, there are stability problems. Stephen Hawking and others have shown that quantum effects would likely cause a traversable wormhole to become violently unstable. Imagine a wave that collapses into infinite density just as you're passing through. Not a pleasant way to travel. There's also the causality problem. A wormhole connecting 2 points in space is also potentially a time machine. If you can traverse space instantly through a wormhole, with some clever manipulation involving relativity, you could potentially use it to travel backward in time. This creates all sorts of paradoxes, the famous grandfather paradox being the most obvious. Could you go back in time and prevent yourself from entering the wormhole? The universe doesn't seem to like paradoxes. Hawking proposed what he called the chronology protection conjecture. Essentially, the laws of physics conspire to prevent time machines from forming. Whenever you get close to creating one, something goes wrong. Quantum fluctuations become infinite. The wormhole collapses. Something happens to prevent the paradox. It's not proven, but it's a reasonable hypothesis. So wormholes, mathematically possible, physically uncertain, practically far beyond our capabilities. They're a theoretical loophole, but not one we can exploit with anything resembling current technology or understanding. Now let's talk about something even wilder. The Alcubierre drive, named after Mexican physicist Miguel Alcubierre, who published a paper in 1994 describing a way to achieve faster-than-light travel without actually moving faster than light. Sound impossible? Here's how it works. Instead of moving your spacecraft through space, you warp space itself. You contract space in front of your ship and expand it behind your ship, creating a warp bubble. Inside the bubble, you're not moving at all relative to local space. But the bubble itself, and you with it, can move arbitrarily fast through the larger universe. Think of it like this. Imagine you're on a moving walkway at an airport. Relative to the walkway, you're standing still. But relative to the airport, you're moving. Now imagine the walkway can move at any speed, even faster than light, and you've got the Alcubierre drive. You're surfing on a wave of space-time. This doesn't violate relativity because you're never moving faster than light through local space. It's space itself that's doing the moving. It's the same principle that allows the universe to expand faster than light space can do whatever it wants. It's only stuff moving through space that has to obey the speed limit. The math works. Alcubierre's equations are valid solutions to Einstein's field equations. NASA scientists, including Harold "Sonny" White at the Johnson Space Center have actually studied this seriously and have even proposed modifications to make the energy requirements less insane. Because here's the problem. Alcubierre's original calculation showed that creating a warp bubble would require negative energy equivalent to the mass energy of Jupiter. That's 1.9 times YY kilograms, converted to pure energy, and it needs to be negative energy exotic matter again. We're back to the same problem as wormholes. White and his colleagues managed to tweak the geometry to reduce the energy requirements by many orders of magnitude down to something like the mass of the Voyager spacecraft. That's still exotic matter we don't know how to create, but it's a lot better than Jupiter. But there are other problems. A 2012 paper by physicists at the University of Sydney showed that as the warp bubble travels through space, it would accumulate particles and radiation in front of it. When you decelerate and the bubble collapses, all of that accumulated energy would be released in a catastrophic burst, essentially destroying anything in front of the ship and possibly the destination itself. Your arrival would be announced by a blast of radiation equivalent to multiple supernovae. Not ideal for visiting new worlds. There are also questions about whether you could actually control such a bubble from inside it. Some calculations suggest that once you're in a warp bubble, you can't send signals to the front of the bubble to steer or stop it, because that would require faster-than-light communication. You'd be trapped in a runaway warp bubble with no way to control or exit it. So the Alcubierre drive, brilliant theoretical work, serious practical problems, relies on exotic matter we don't know how to create, and may have additional physical limitations we haven't fully understood yet. Are you noticing a pattern? Every loophole seems to require exotic matter or negative energy, and we genuinely don't know if it's possible to create or harness such things in the quantities required for interstellar travel. But let me tell you about one more theoretical possibility, and this one doesn't require exotic matter. Generation ships. Not a physics loophole, but a biological and sociological one. If we can't travel fast enough to reach distant stars in a human lifetime, we build ships large enough to sustain human populations for multiple generations. The people who leave Earth aren't the ones who arrive at the destination. Their great-great-great-grandchildren are. The concept has been around since the early 20th century, explored by scientists like J.D. Bernal in the 1920s, and later popularized by Robert Heinlein in science fiction. The idea is straightforward. Build a ship large enough to sustain a closed ecological system, populate it with several thousand people to maintain genetic diversity, and send it on a multi-century journey to another star. People are born, live their lives, and die on the ship. It becomes a traveling world. The advantage: you don't need relativistic speeds. You can travel at whatever speed you can manage. Even 1% of light speed would work, because time is no longer the limiting factor. A journey of 10,000 years is fine if you have 300+ generations living on the ship. But the problems are immense. 1. Engineering. The ship needs to be completely self-sufficient for centuries or millennia. Everything must be recyclable air, water, waste. Closed ecological systems are extremely difficult to maintain. We've tried building small ones on Earth, Biosphere 2 being the most famous example, and they've all failed or required external input. Scaling up to a working system for thousands of people for thousands of years is extraordinarily difficult. 2. Social stability. Can a human society remain stable and focused on its mission for hundreds of generations? People born on the ship never chose to be there. They're confined to a limited space for their entire lives. Historical experiments with isolated communities suggest that social breakdown, conflict, and loss of mission focus are serious risks. What if a generation decides they don't want to continue? What if the society fragments or descends into civil war? 3. Genetic diversity. You need enough population to avoid inbreeding depression, but not so many that resource requirements become impossible. Studies suggest you'd need at least 500 people to maintain genetic diversity and preferably several thousand. But more people mean a larger ship, more resources, more complexity. 4. Knowledge preservation. Over generations, technical knowledge could be lost. The people who arrive need to know how to land, how to establish a colony, how to survive. But if you're 150 generations removed from Earth, do you still have that knowledge? Languages change, cultures drift, information gets lost. How do you ensure continuity of knowledge over such timescales? 5. Psychological effects. Humans evolved in open environments with natural rhythms, weather, ecosystems. What does it do to human psychology to live in an artificial habitat for your entire life, knowing you'll never see Earth, never experience a planet? Studies of submariners, Antarctica researchers, and astronauts show that isolation takes a severe psychological toll, even over short periods. Some proposals suggest putting the crew into cryogenic suspension or hibernation for most of the journey, only waking them up periodically for maintenance or when they near the destination. But we don't have working cryogenic suspension technology. Every attempt to freeze and revive mammals has failed. The formation of ice crystals ruptures cells. Some animals like tardigrades and wood frogs can survive freezing, but they have special adaptations we don't. Creating such technology for humans is, at best, many decades away and possibly impossible. So even the generation ship concept, which seems like it should be more feasible than warp drives or wormholes, presents overwhelming challenges. Here's where we are. Physics provides no way to travel faster than light through space. It might provide ways to bend or shortcut through space, but those ways require exotic matter we can't create. Slower than light travel faces enormous engineering, biological, and social challenges. And even if we solve all of those problems, the expansion of the universe means most of the cosmos is unreachable regardless. It's enough to make you despair. But here's the thing. These limitations apply to biological humans traveling through space in conventional ways. What if we change our assumptions? What if human space travel doesn't mean sending biological humans? What if we modify humans for space? What if we send something else entirely? That's the next rabbit hole we're going down, and it's going to challenge your assumptions about what it means to be human and what it means to explore. Stay with me. Let's talk about the solutions that most people don't want to hear, but that are increasingly being discussed seriously by scientists and futurists. Maybe biological humans aren't meant to explore deep space. Maybe we need to change what we are, or send representatives of humanity that aren't biological at all. This is going to get philosophical, ethical, and weird. But I need you to really think about this. When we ask, how far can humans travel into space? There's an implicit assumption that human means the biological organism Homo sapiens as currently configured. But what if that assumption is the problem? What if the solution to space travel is not better spaceships, but different humans? Let's start with the most conservative option, genetic modification. We could, in principle, genetically engineer humans to be more resistant to space conditions. Increase bone density, improve DNA repair mechanisms to handle radiation better, modify the cardiovascular system to work better in microgravity, enhance muscle regeneration. We already have gene editing technology, CRISPR-Cas9, discovered by Jennifer Doudna and Emmanuel Charpentier, Nobel Prize in Chemistry, 2020, that allows precise editing of DNA. Some researchers are already discussing the concept of space-adapted humans, people who are genetically optimized for life in space, potentially at the cost of being less adapted for life on Earth. Maybe they have denser bones, different bone structure, more efficient oxygen use, better radiation resistance. These modifications could be made to embryos before birth, creating a generation literally born for space. But this raises massive ethical questions. Who decides what modifications to make? What if the modifications have unexpected negative effects? Are we creating a separate subspecies of humanity? What are the rights and status of genetically modified humans? Many countries have banned human genetic modification for anything beyond preventing serious diseases. And for good reason, the potential for abuse is enormous. But put ethics aside for a moment and just consider feasibility. Even with genetic modification, we're still talking about biological organisms with biological needs. You still need food, water, air, waste processing. You still age and die. You're still vulnerable to disease and injury. Genetic modification might make space travel less deadly, but it doesn't fundamentally solve the distance and time problems. So let's go further. What about cybernetic enhancement? Replacing or augmenting biological systems with mechanical ones. Need more radiation resistance? Replace skin with engineered materials. Need to survive longer without food? Add energy storage systems to the body. Need to repair damage? Include nanobots in the bloodstream. This is the realm of transhumanism, the philosophy and movement that advocates using technology to enhance human physical and cognitive capabilities beyond current biological limits. Proponents like Nick Bostrom and Ray Kurzweil argue that such enhancement is not only possible, but inevitable and desirable. A cybernetic human part biological, part machine could potentially survive conditions that would kill an unmodified human. You could replace the need for constant breathing with more efficient oxygen storage and CO2 scrubbing. You could replace fragile biological organs with more durable mechanical ones. You could potentially even address the aging problem, extending lifespan dramatically. But at what point do you stop being human? If you've replaced 60% of your body with machinery, are you still the same person? This is a modern version of the ancient ship of Theseus philosophical paradox. If you gradually replace every part of a ship, is it still the same ship? If you gradually replace every part of a human, are they still the same human? And we still haven't solved the fundamental time and distance problems. Even a cybernetic human would take decades, centuries, or millennia to cross interstellar distances. You'd need to address the mortality problem completely, which brings us to the next possibility, uploading consciousness. This is the idea that the you that matters, your memories, personality, thought patterns, could be transferred from your biological brain to a computer substrate. Your mind runs on hardware that's far more durable and maintainable than biological tissue. Is this possible? We genuinely don't know. It depends on whether consciousness is something that can be copied or whether it's fundamentally tied to specific physical substrate. The philosopher David Chalmers calls this the hard problem of consciousness. We don't actually understand how physical processes in the brain give rise to subjective experience. We don't know if uploading would preserve you or just create a copy that thinks it's you while the original you dies. But suppose it's possible. Suppose we can upload human consciousness into sophisticated computers. Now you've solved the biology problem completely. No need for food, water, or air. No vulnerability to radiation, at least not biological vulnerability. Electronics can still be damaged by radiation, but they're more resistant and easier to shield. No aging. You could potentially exist for as long as your hardware is maintained. An uploaded consciousness could survive journeys of arbitrary length. A million-year journey to a distant galaxy? No problem. You could even be paused, shut down during travel, and reactivated upon arrival. From your subjective experience, the journey would be instantaneous. But this raises profound questions. Is an uploaded consciousness still human? Does it have human rights? Can it still be said to experience anything, or is it just a simulation? And most troubling, even if you can upload a consciousness, can you copy it? Could you make multiple copies of one person? Would they be the same person? Different people? Do they each have individual rights? And here's the practical problem. Uploaded consciousness still requires hardware, and that hardware is in space traveling to distant stars. It needs power, protection from cosmic rays, maintenance. If something goes wrong, you could lose the entire consciousness permanently. You've put all your eggs in one very fragile basket. Let's go even further. What if we don't send humans at all, uploaded or otherwise? What if we send machines, artificial intelligences, as our representatives? An AI could be designed specifically for space travel. No biological vulnerabilities, no psychological need for Earth-like environments, no lifespan limitations. An AI could potentially survive millions of years with proper maintenance and redundancy. We could send AI probes to explore the galaxy, gathering information and sending it back to Earth. Each probe could be small, fast, and cheap. We could send millions of them. Some would fail, but many would succeed. Over time, we'd build up an enormous database of information about the galaxy without ever leaving Earth ourselves. This is actually the most feasible near-term approach to exploring beyond our solar system. The Breakthrough Starshot initiative I mentioned earlier is essentially this: tiny AI-guided probes traveling at relativistic speeds to nearby stars. They can't carry humans, but they can carry cameras, sensors, and enough computing power to make decisions autonomously. But this raises an interesting question. If we send AI representatives to explore the galaxy, is that still human space exploration? Have humans traveled to distant stars if only our robot emissaries have been there? Or does it only count if biological humans make the journey? This might seem like semantics, but it's actually crucial to how we think about space exploration. When we dream of exploring the galaxy, what are we really dreaming of? Is it the gathering of information and knowledge? Or is it the human experience of being in those places, touching alien soils, seeing alien suns with our own eyes? There's a proposal called the von Neumann probe concept, named after mathematician John von Neumann, who first described self-replicating machines. A von Neumann probe is a spacecraft that can reproduce itself using materials it finds in space. You send one probe to a star system. It arrives, mines asteroids for raw materials, builds copies of itself, and sends those copies to other star systems. Each of those copies does the same thing. The number of probes grows exponentially, and within a few million years, a blink of an eye in cosmic terms, you've explored the entire galaxy. The brilliant thing about von Neumann probes is that you only need to build one. That one probe does all the work of reproduction and exploration. The exponential growth means that even with slow travel times between stars, the galaxy gets explored relatively quickly. The disturbing thing about von Neumann probes is that we don't see any. If such probes are possible, and if any other intelligent civilization in our galaxy has ever built them, they should have spread across the galaxy by now, and we should have encountered them. The fact that we haven't is part of the famous Fermi paradox. Where is everybody? Either von Neumann probes are impossible for some reason we don't understand, or no civilization has ever built them, or civilizations don't last long enough to build them, or they've been here and we didn't notice, or the unsettling option, we're the first civilization capable of building them. But I'm getting off track. The point is, we have lots of options for exploring space that don't involve sending biological humans. We could send modified humans, cyborgs, uploaded consciousness, artificial intelligences, or self-replicating probes. Each option has different capabilities and limitations. Each raises different philosophical questions about what counts as human exploration. And here's the thought that should really bake your noodle. Maybe the solution is all of the above. Maybe humanity's expansion into space isn't about one approach, but many. Biological humans terraform and settle nearby worlds like Mars. Genetically modified humans colonize more challenging environments. Cyborgs venture into regions where full biology can't survive. Uploaded consciousnesses travel to distant stars. AI probes explore even farther. Each approach suits different contexts. In this view, humanity doesn't explore space as a single unified thing. Humanity diversifies, branching into multiple forms, each adapted to different environments and goals. The future of humanity might not be singular, but plural many different types of beings, all descended from or created by Homo sapiens, all carrying some aspect of human culture and knowledge forward. This is simultaneously exciting and unsettling. It means the question, how far can humans travel into space, doesn't have one answer. It has many, depending on which type of human we're talking about. But all of this assumes we develop these technologies. And that brings us to a darker question. Will we? Do we have the time, resources, and stability to develop space travel before something else, climate change, war, pandemics, societal collapse prevents us from doing so? This is what some scholars call the great filter problem, part of the Fermi paradox. If intelligent life is common in the universe, but we don't see evidence of widespread spacefaring civilizations, maybe there's a filter challenge that most civilizations fail to pass. Maybe the filter is behind us. Developing intelligence is incredibly rare. Or maybe it's ahead of us. Civilizations tend to destroy themselves or hit some developmental dead end before they can colonize the galaxy. If the filter is ahead of us, then the question, how far can humans travel into space, might have a simple, dark answer. Not very far, because we won't last long enough to develop the technology. But let's not end on that pessimistic note. Let's assume we survive. Let's assume we develop the necessary technologies. How far could we actually reach? What's the practical limit? Here's my synthesis of everything we've discussed. With current technology, barely beyond our solar system. We've sent probes to the edge of the solar system and beyond, but human travel is limited to near-Earth orbit. With plausible near-future technology, next 100 to 200 years. Nearby stars within 10 to 20 light years, probably using light sails, nuclear propulsion, or generation ships. We're talking about the immediate stellar neighborhood. With advanced technology, exotic matter, warp drives, etc., if they're possible, potentially anywhere within our local galaxy cluster, the Laniakea supercluster. That's about 100,000 galaxies within 520 million light-years. With any technology consistent with known physics, nothing beyond our local supercluster due to cosmic expansion. The ultimate, absolute, physical limit on human space travel is set by the expansion of the universe itself. And that limit is closing. We exist in a brief cosmic moment billions of years after the Big Bang, but potentially only trillions of years before the universe becomes dark, cold, and empty, when interstellar travel is difficult, but theoretically possible. If we wait too long, even that possibility closes. Which brings us to the most important question of all, the one we've been building toward. Given all these limitations, why should we even try? What's the point of space exploration if we can only reach a tiny fraction of the universe? Why does it matter? That's what we're tackling next, and it's going to transform how you think about humanity's place in the cosmos. Now we need to talk about why any of this matters. Because after everything I've told you, all the limitations, all the impossibilities, all the barriers, you might be thinking, why bother? If we can only reach a tiny fraction of the universe, if the challenges are so immense, why should humanity even try to explore space? This is the personal connection moment. This is where we talk about why the question, how far can humans travel into space, isn't just about distances and technologies. It's about who we are as a species, what we value, and what legacy we want to leave. Let me start with the practical arguments, then we'll move to the profound ones. First, practical survival. Earth will not be habitable forever. In about 1 billion years, the sun will have brightened enough that Earth's oceans will evaporate. In about 5 billion years, the sun will expand into a red giant and engulf Earth entirely. These timescales seem impossibly distant, and they are by human standards, but they're absolute deadlines. If humanity remains confined to Earth, humanity has an expiration date. Long before that, we face more immediate existential risks: asteroid impacts, supervolcano eruptions, pandemics, nuclear war, climate change, artificial intelligence risks. Any one of these could end human civilization if not managed carefully. Having human populations on multiple worlds, becoming a multi-planetary species dramatically, reduces the risk that a single catastrophe could end humanity entirely. It's the old wisdom of not putting all your eggs in one basket, scaled up to planetary proportions. But this practical argument, while valid, doesn't really capture the deeper importance of space exploration. Let me give you the arguments that actually matter, the ones that touch on something fundamental about human nature. Argument 2. Exploration is part of what makes us human. Think about human history. We evolved in East Africa. We could have stayed there. It's a perfectly good place to live, even today. But we didn't. We spread across the planet, crossing oceans, deserts, ice sheets, mountains. We settled in environments ranging from tropical rainforests to Arctic tundra. We went to places that seemed impossible, the depths of oceans, the peaks of mountains, the polar ice caps. Why? Practical resources are part of it, but not all of it. There's something in human nature that drives us to explore, to see what's beyond the horizon, to go where no one has gone before. It's related to curiosity, to adventure, to the desire to test ourselves against challenges. This drive is so fundamental to human psychology that we feel its absence. People in unchanging, unchallenging environments become depressed and listless. We need frontiers, physical or intellectual, to feel fully alive. Space is the ultimate frontier. It's the one that will never be exhausted. No matter how far we go, there's always farther. No matter how much we discover, there's always more to discover. If humanity stops exploring space, we're essentially saying we've decided to stop being the kind of species we've always been. Argument 3. Space exploration drives innovation. This is well documented. The Apollo program, despite its relatively short duration, produced thousands of technological spin-offs. Everything from satellite technology to computer miniaturization to medical devices benefited from technologies developed for space. The International Space Station has been a testbed for technologies in materials science, fluid dynamics, combustion, and human physiology. GPS, weather forecasting, global communications, Earth observation for climate science all depend on space technology. But it's not just about spin-offs. It's about what happens to human ambition when we set seemingly impossible goals. President John F. Kennedy's 1962 speech, setting the goal to land a man on the moon and return him safely to Earth before the end of the decade, mobilized an entire generation. It inspired people to study science and engineering, to push boundaries, to think bigger. The goal itself, reaching the moon, was in some ways less important than what achieving that goal did to our collective psyche. It showed us that if we commit to something fully, if we marshal our resources and intelligence, we can do things that seem impossible. Space exploration does this. It gives us goals that require stretching beyond our current capabilities. It forces us to solve problems we've never faced before. It makes us better than we otherwise would be. Argument 4, and this is where it gets profound. Space exploration gives us perspective. There's a phenomenon that astronauts frequently report called the overview effect, a term coined by space philosopher Frank White in 1987. When astronauts see Earth from space, this small, blue, fragile sphere floating in the vast darkness, something changes in their perception. They describe a cognitive shift, a deep emotional and intellectual realization of Earth's fragility, of the unity of humanity, of the preciousness of life. Astronaut Edgar Mitchell, who walked on the moon during Apollo 14, described it this way. You develop an instant global consciousness, a people orientation, an intense dissatisfaction with the state of the world, and a compulsion to do something about it. From out there on the moon, international politics looks so petty. You want to grab a politician by the scruff of the neck and drag him 250,000 miles out and say, "Look at that, you son of a bitch." That perspective, that visceral understanding of Earth as one interconnected system, of humanity as one species sharing one small world is transformative. And it's something that only space exploration can provide. Every photo of Earth from space, every video transmitted from the Moon or Mars, every expansion of our cosmic perspective helps humanity see itself more clearly. And it's not just about Earth. It's about understanding our place in the cosmos. For most of human history, we thought Earth was the center of the universe. Then we learned we orbit the sun. Then we learned the sun is one star among hundreds of billions in our galaxy. Then we learned our galaxy is one among trillions. Each expansion of knowledge has been humbling and enlightening. We're not the center of the universe. We're not even the center of our galaxy. We're a small species on a small planet orbiting an ordinary star in an ordinary galaxy in an ordinary part of the universe. But here's the paradox. That knowledge doesn't make us insignificant. It makes us more precious. Because as far as we know, we're the only part of the universe that can understand the universe. We're the universe becoming conscious of itself. We're matter organized in such a way that it can look out at the cosmos and comprehend what it sees. That's extraordinary. Carl Sagan, in his famous Pale Blue Dot, reflection on a photo of Earth taken by Voyager 1 from 4 billion miles away, captured this beautifully. Look again at that dot. That's here. That's home. That's us. On it, everyone you love, everyone you know, everyone you ever heard of, every human being who ever was, lived out their lives. On a mote of dust suspended in a sunbeam, space exploration confronts us with our cosmic context. It forces us to ask big questions. Are we alone? Is there other intelligent life? How common is life? How does consciousness arise? What is our responsibility as possibly the only technological species in our galaxy? These aren't just abstract philosophical questions. They have implications for how we live, what we value, what we strive for. Argument 5. Space exploration is our story. It's not just a thing some scientists and engineers do. It's part of humanity's narrative. Every culture has stories of exploration and discovery. Every child looks up at the stars and wonders. Space exploration is the continuation of a story that's been unfolding for hundreds of thousands of years. It's the next chapter in the human journey. And here's something most people don't realize. You're part of this story, whether you think you are or not. You live in a civilization that has sent robots to Mars, that has had humans living continuously in space for over 2 decades, that has probes leaving the solar system carrying greetings from Earth. You live in the first moment in human history when this is true. You're alive during the first baby steps of human space exploration? Think about that. For all of human history, until about 70 years ago, space was unreachable. It was the domain of gods and myths. Now we have footprints on the Moon. We have rovers on Mars. We have a helicopter flying in the Martian atmosphere. The Ingenuity helicopter that flew in 2021, proving that powered flight is possible on another world. We have telescopes like James Webb showing us the universe in unprecedented detail, looking back to the earliest galaxies formed just hundreds of millions of years after the Big Bang. You're witnessing the birth of space exploration. You're alive during the moment when humanity transitions from a single planet species to something more. Whether or not you personally go to space, whether or not you work in the space industry, this is happening in your lifetime, and it's significant. But let me make this even more personal. Let's talk about what space exploration means for your daily life, your worldview, your sense of meaning. Modern life can feel small sometimes. You go to work. You pay bills. You deal with daily stresses. It's easy to get trapped in a narrow focus, to forget the bigger picture. Space exploration, even just being aware of it, following it, understanding it, provides that bigger picture. It reminds you that humans are capable of incredible things. It reminds you that we're part of something larger than our individual lives. There's a psychological benefit to this. Studies have shown that people who feel connected to something larger than themselves, a community, a cause, a story are happier, more resilient, and more motivated. Space exploration provides that connection. When you read about a Mars rover discovering evidence of ancient water, you're not just learning a fact, you're participating in humanity's grandest adventure. You're part of the species that does this. And it provides hope. In a world of political division, environmental crisis, and social challenges, space exploration reminds us that humans can cooperate on ambitious projects. The International Space Station involved 5 space agencies from 15 countries. The James Webb Space Telescope was a collaboration between NASA, the European Space Agency, and the Canadian Space Agency. When we reach beyond Earth, we often do it together, setting aside differences in pursuit of shared goals. Space exploration shows us our potential. It shows us what we can be when we're at our best. Now, let me address the criticism that I know some of you are thinking. This is all well and good, but shouldn't we fix Earth's problems before we worry about space? Isn't it morally wrong to spend resources on space exploration when people are hungry, when climate change is a threat, when we have so many urgent problems here? This is a legitimate concern, and it deserves a serious answer. Here it is. Space exploration and solving Earth's problems are not in competition. They're synergistic. First, the resources spent on space exploration are a tiny fraction of global spending. NASA's budget is about 0.5% of the U.S. federal budget. Globally, all space programs combined are less than 0.1% of global GDP. We're not talking about a major reallocation of resources. For comparison, the world spends vastly more on military expenditures, entertainment, or advertising than on all space programs combined. Second, space technology directly helps with Earth's problems. Satellite monitoring of climate change, deforestation, and ocean health, GPS for efficient transportation, weather satellites for disaster prediction, communications satellites for connecting remote areas. These are all space technologies that address Earth problems. Third, the mindset and capabilities we develop for space exploration make us better at solving problems in general. The engineering, the long-term thinking, the systems approach, the innovation, these skills transfer. Many people who work on climate solutions, on sustainable energy, on global health challenges got inspired by space exploration. The mindset of, let's solve this seemingly impossible problem, is valuable whether the problem is reaching Mars or achieving carbon neutrality. But most importantly, humanity is capable of doing multiple things at once. We don't have to choose between feeding the hungry and exploring space. We can and should do both. We're a species of billions of people with vast resources and capabilities. The question isn't space or Earth. It's how do we allocate our resources wisely to do everything we need to do. And here's a subtle point. If we lose our ambition for the difficult and long term, if we become a species that only focuses on immediate problems and survival, we lose something important. We lose our sense of purpose and possibility. A civilization that looks only inward, that has no frontier, no sense of expanding possibility, tends to stagnate. The very act of reaching for space, of maintaining that ambition, keeps us vital and forward-thinking in all areas. So when someone asks, why explore space when we have problems on Earth? The answer is, because we're human, and humans explore. Because the technologies we develop for space help on Earth. Because having ambitious goals makes us better. Because Earth's problems don't go away by ignoring space. They get solved by capable, inspired people, and space exploration creates such people. Now let me bring this to a conclusion with the biggest idea of all, the one that ties everything together. The question, how far can humans travel into space, is really asking, what are the limits of human possibility? And the answer is, we don't know yet. We know there are physical limits, the speed of light, the expansion of the universe. We know there are biological limits, at least for unmodified humans. We know there are technological limits based on our current capabilities. But we don't know where the ultimate limits are. We don't know what discoveries await us in physics, in biology, in engineering. We don't know what technologies we'll invent in 100 or 1,000 years. We don't know what we're truly capable of as a species, because we've only just begun. The history of humanity is a history of overcoming limits that seemed absolute. Human-powered flight was impossible until it wasn't. Breaking the sound barrier was impossible until it wasn't. Leaving Earth was impossible until it wasn't. Walking on the moon was impossible until it wasn't. Every generation faces limits and assumes some of them are absolute. And every generation is proven partly wrong by the next generation. This doesn't mean all limits can be overcome. Some are truly fundamental. It means we should be humble about declaring what's ultimately impossible. So when we ask how far humans can travel into space, the honest answer is, we don't know. We know the lower bound. We can definitely reach the moon, probably Mars and the outer solar system, likely nearby stars within decades or centuries. We know there's an upper bound set by cosmic expansion. But where exactly the practical limit lies between those bounds depends on choices we haven't yet made, technologies we haven't yet invented, and potentially even on changing what we are. And that uncertainty, that open question, is beautiful. It means the future isn't written. It means we have agency. It means that what humanity achieves in space depends on what humanity chooses to do. Every one of you listening to this is part of that choice. Whether you become an engineer working on spacecraft, a scientist studying other worlds, a teacher inspiring the next generation, a citizen supporting space programs through taxes and votes, or simply someone who looks up at the stars and dreams, you're part of humanity's relationship with space. The question isn't just, how far can humans travel into space? It's, how far will we choose to travel? And that's up to us. So here's my challenge to you. Let this knowledge change how you see the universe. Let it change how you see yourself. You're not just a person living a life on Earth. You're a member of a spacefaring species, possibly the only one in our galaxy, with both the capability and the responsibility to explore, to understand, to preserve consciousness in the universe. When you look up at the night sky, you're not just seeing pretty lights. You're seeing destinations. Most of them impossible to reach, yes, but some of them the nearest ones possible. Difficult, challenging, requiring perhaps centuries of work and innovation, but possible. And beyond the reachable stars are the unreachable ones, billions upon billions of them, forever beyond our grasp due to cosmic expansion. But here's the profound part. We can still see them. We can still study them. We can still know they're there. The universe has given us enough capability to understand our limitations, to grasp the cosmic context, to see the full scope of reality, even if we can't visit all of it. That's a gift. That's a kind of cosmic grace, that we get to understand the universe, even from our limited vantage point on this small world. So my final message is this: be curious. Support space exploration, whether with your career, your votes, your attention, or just your wonder. Pass on that curiosity to the next generation. Humanity's journey into space is just beginning, and it needs people who care, who dream, who understand why it matters. Because ultimately, space exploration is an expression of hope. It's a statement that we believe humanity has a future, that we're worth preserving, that what we've learned and created and become is precious enough to carry forward into the cosmos. In a universe that seems indifferent, that operates on timescales that dwarf human lives, that will eventually end in darkness and entropy, the fact that we conscious beings, capable of love and wonder and understanding exist at all, is miraculous. And the fact that we can look outward, ask questions, seek answers, and push boundaries, even knowing our limits, that's not just survival. That's not just curiosity. That's meaning. That's purpose. How far can humans travel into space? As far as we choose to, within the constraints physics allows. And that distance, whatever it turns out to be, will be a measure not just of our technology, but of our ambition, our courage, our wisdom, and our determination to ensure that consciousness, this brief, bright flame in the cosmic darkness, burns as long and as brightly as possible. Thank you for taking this journey with me. If this changed how you see space, how you see humanity, how you see your own place in the cosmos, then it was worth it. And if you want more content like this deep dives into the biggest questions science can ask, make sure you're subscribed. Now go look up at the stars, knowing what you know. They'll never look quite the same again.